Okay, so here's the agenda for today. Basically, it focuses on this SDR platform. So first, I will give you what is overview of what is SDR, and then we'll take a look at how we can design this SDR, the workflow in MATLAB and Simulink. And before I summarize, I also provide you further resources if you want to learn more on this. Okay, so let's start with SDR. What is SDR, software-defined radio system? Basically, to put it in simple terms, it's just a radio which some of the all physical layer function are software-defined or software program. Okay? So if you know, radio is just a device that help you to transmit and receive the signal wirelessly in RF spectrum. And the programmability part of this SDR system allows you to easily add a new functionality or even do the upgrade remotely at any point in time, and also reuse a part of your algorithm. Okay, so how we can feel of this system? Basically, it consists of this RF front end. Basically, you have this direct RF conversion with local oscillator or mixer. Then you have the DC or DAC part of it. Then in the middle portion, where you have this digital front end, basically you are responsible for this high rate digital signal data processing, like you have a DDC or a digital up converter, okay, part of it. And then on the right side is your baseband processing, which connect to your local desktop or for your simulation part. Okay, so we can think that this system can be built from commercial off-the-shelf hardware. So these are typical example, like for front end, maybe you have this FMC-based tunable RF card connected to this FPGA, or if you're using a system on chip board, then for baseband processing is your computer, the host computer that running this the simulation. Okay, so then the connection or the interface between the host computer with this the card could be one of the interface using the gigabit Ethernet, where allows you to tune the RF parameter or the center frequency of your particular operating RF system. So why is important that we take a look at this implementation workflow for SDR? As you may know that radios are been around many years, or they are everywhere. But with addition to this traditional application where normally radio are being used, we've seen that there's a rapid growth in a new application area of wireless communication, like where, like for example, you have now a surveillance system, or a smart metering, or even the medical monitoring system that using this wireless technology. And also with the emergence of new wireless standard like a 5G or the existing LTE or P2X have been enabled of this booming of this radio application. Okay, so with this, we see that this system need to have a higher adaptability that allows you to quickly design and simulate or prototype various radio. So in this case, we think software-defined radio system can be considered as a solution for this type of application. Okay, so with this SDR itself, definitely it also have challenges when want to design this SDR system, or even to implement the system. You can see that in this slide here, basically, in order to design a robust SDR system, basically you need to require many multiple skill set, like from designing your antenna, RF portion, baseband, or DSP part, or even the come out with the hardware software architecture design, like FPGA, and also your embedded software development, just to name a few. So if each of these domain definitely has its own skill set, okay, and also use a different design environment. Okay, so it becomes practically difficult for one to be expert in all area. So that's why there's a need for, in order to have a common design environment that can address these multiple areas. And that's where today's session, where we discuss how we can use MATLAB and Simulink as a common platform, development platform to address different multi-domain for this SDR development. So before we get started to look at the SDR workflow, maybe I just point you to one particular user story from our customer who used this our solution. So this customer is Orolia, is a leader in developing the resilient positioning on navigation and timing solution. Okay, so what they did is they are expert in this communication system area, but they might lack in certain skill in FPGA development. So using they adopt our workflow, like using model-based design with MATLAB and Simulink, and also using the HDL coder, they can easily target and generate the HDL code for FPGA implementation. Then with this, they can see the implementation time cut off at least by 50%. Okay, then also the analysis and testing part also shortened by 8 months. So you can see using the workflow that I'll present shortly, that there's an advantage and in terms of development cycle. Okay, so now let's discuss the design cycle or design workflow for this SDR. So basically, we can define the SDR workflow into 4 stages. First, on the top left, you can see basically we do the entire system modeling in MATLAB and Simulink. Okay, so this is where we can quickly analyze the performance, or even find out any potential design issue earlier. And once the algorithm developed at this stage, we will move on to test it with real signal. Okay, real signal, in this case, we replace the RF transmitter model with a real devices or chip. Okay, then we can test with a real scenario or real signal. Then once we can verify this portion here, our baseband algorithm, then we can also replace again and implement this our algorithm to the FPGA or even the processor. Okay, so in this case, for the quick prototyping. Okay, once this already we gains confidence that our model or our algorithm works perfectly and it meets our requirement and criteria, then we can move on to the last stage, where basically we implement everything in the hardware and it become the standalone this hardware. Okay. So we'll take a look at each design cycle. So the first step here basically is a modeling and simulation of the entire signal chain, where we have not only the baseband processing, but how we can model the RF. So in MATLAB and Simulink, basically you can design the entire signal chain. MATLAB and Simulink provides the ability for you to model this multi-domain system in a single environment. Therefore, it allows you to analyze this interrelationship between different components and see how one affects the others. Okay? The performance of one system affect the others. Also, you can easily generate host of multiple waveform, like either the standard compliant waveform or even the custom waveform. And then you can also design this or the architect your RF front end, which you can also include the non-linearity effects in your system. Then you can. So in this case, maybe you can design your ADC, DAC, and you can also integrate with the antenna channel propagation. So you can analyze the entire thing. Okay, so in terms of waveform generation in MATLAB, it provides a rich of library for you to quickly and easily generate these different type of waveform, like from a standard compliant waveform like a 5G LTE, wireless LAN, Zigbee, Bluetooth, just to name it, and also custom waveform as well. So in terms of like doing the end-to-end physical layer simulation, we can do the complete physical layer development starting from waveform generation that I mentioned just now. You can also include this RF impairment, put the effect of the channel and RF impairment analysis, and then you can design a practical receiver. So there are several examples provided in MATLAB website that help you to choose which one that you want to design. Like maybe you want to design a standard wireless system or non-standard base. These are a good reference for you to use as a starting point for your wireless system design. Okay, so all these examples are available in form either in a MATLAB code or a Simulink model that you can easily configure or modify according to your system requirement. So we can also improve the fidelity of this RF front end. So you can see that in typical system modeling, we include this effect of non-linearity, but we can improve further that we have the block to represent this RF part here. The RF front end is simulated using our tools like RF Blockset, where it allows you to do the closed loop simulation with a baseband and this the RF together. So this is a typical snapshot of your RF portion. Okay, then you can also doing the analysis like doing the EVM computation. So there are also numerous models that are available from our library. In this case, if you use this analog device RF transceiver, we already have a model for it like AD9361, the Agile RF transceiver operating from 70 megahertz up to 6 gigahertz. So for this, this behavioral model that we developed in MATLAB and Simulink has been tested against the real hardware, okay, in the lab setup. Then we observe that or we validate this model to be a close match between the physical hardware and this model. So in case if you are working on SDR platform that using this RF transceiver, you can directly incorporate this model to your baseband algorithm design. Okay, so there are also a number of reference examples that show how you can connect your baseband processing with this transceiver model. So one of these examples that I'll show you is so this one. Basically, in this demo, basically I have this QPSK. It's just a QPSK modulation scheme in my baseband portion that I connect to this AD9361 transmitter. Then also coming to this channel model is in turn connected to this 9361 receiver as well. Then we perform this the demodulation. You can see from the constellation, and also doing this error rate calculation. So a closer look of this model of this AD9361. You can see, oh, sorry. Okay, so a closer look of this model is the one that I show you in a previous slide, basically how we can represent this block or subsystem with the block from our RF block set. So if you are interested in this particular model, that there's a link for you to download this from this page here. Okay, so in case you're also working with custom RF front-end design, there are also multiple examples that show you how we can simulate this the practical radio of this RF transmit and receive. So for different type of system like LTE, wireless LAN, or 5G, as well as non-standard protocol-based radio. Okay, so you can see from this few example here, in case if you need this information. Okay, so now the next part here, or the next aspect of this software-defined radio development. Basically, once we simulate the entire system in MATLAB and Simulink, then we can replace the RF portion part with the real RF transceiver. And doing this, by doing this, basically we can get the real life streaming RF data directly into MATLAB and Simulink. Okay, then we can verify our algorithm, the baseband processing in MATLAB and Simulink. So how we can do this? Basically, in MATLAB, we have this capability to connect with various RF instrument and even the SDR platform directly for this over-the-air testing and verification with this real RF signal. So you can get close to near real-time streaming of RF data to the MATLAB. The reason I say is near because the throughput is limited by this the interface, or in this case the Ethernet transport rate, okay, and the host computer performance as well. You can also capture the continuous burst of sample data and use it for your further downstream analysis. So how you can do this? Basically, we have through this support package that help you to connect to with various SDR platform. So in the next slide, you can see these are supported SDR platform for this over-the-air testing and RF signal, capture the RF signal, the air testing process. So beside the this typical low cost like Adam Pluto, we also support like a Xilinx based radio. So far what we have seen basically up to now is the first aspect of the SDR design is basically we design the entire system in MATLAB and Simulink. And then the second one where we test it with a real life signal. Okay, the next step here is basically we want to partition our algorithm or for quick prototyping to this hardware or the platform. Okay, so for our algorithm, how we can partition in which part goes to the FPGA, or then which part go to the ARM processor in case if you using this SoC platform. Okay, so we have this tool that help you to automatically generate the code directly from either your MATLAB algorithm or even the Simulink model. So in this case, if you are targeting the FPGA, we have the tools like HDL coder that generate the HDL code target for this FPGA, and then this embedded coder that help you to generate the code, the C++ code target to this ARM processor. Okay, so before we discuss further on the code generation part, basically what we have looked so up to now is from the system level or come up with this system level algorithm where we design in MATLAB and Simulink. But basically, when we want to target to the hardware, basically the process is quite different. So in system perspective, basically when we design our algorithm in MATLAB and Simulink, basically we're working with a floating point data type and also a factor of array of data. Okay, but come to this hardware implementation. So normally what we need to deal with is a streaming bits of the data that coming to our hardware, and also for FPGA sometimes we need to convert to the fixed point representation. Okay, so basically these are two different way of design from system level and hardware design or hardware architecture. Okay, so in order to bridge this gap, what we can do in MATLAB and Simulink, okay, basically we can help to ease the process. Okay, this through a couple of steps here that I'll show you shortly. So this is the workflow. Basically, what we so far what we design our algorithm or in MATLAB and Simulink, basically we can consist of three parts here. The first part on the left, basically we have the stimuli, the different type of input or waveform inject to our algorithm. Okay, so the second part is where we design our algorithm, and the third part is where we do the verification or analysis. Okay, so when we can, for each part of this, we can easily like just write a test script to design these test cases or the input stimuli, okay, to generate multiple input stream to our algorithm, and similar for the verification and analysis, we also can write the script. But coming to this now the important part when we want to implement to the hardware, we need to modify our algorithm in order to incorporate this to change to a sample based or a string based processing. Okay, so in this slide, the next slide here, we can see from our wireless our reference algorithm in MATLAB and Simulink, then we modify it so that it can work in incorporate this hardware architecture. So what I mean here is basically we need to modify that so that it will work in for this sample processing, okay, or sample based processing. And also we need to another aspect here when we work with a hardware implementation, basically we need to decide the starting point, okay, the starting and the ending part, and also in between whether we capture the valid data. So basically we can design our control signal for this implementation. Okay, so once we modify our algorithm in order to work with sample-based processing, and then we also include this control signal. The next step here is basically doing this fixed point conversion, like I mentioned earlier. Okay, so in MATLAB and Simulink, it helps you to modify your data type from floating to fixed point, which are typically being used for this hardware like FPGA and the ARM processor. So in this case, it's important that we need to choose the right set of fixed point data type, because it not only control the accuracy of our algorithm, but it also determine the amount of resources in our hardware being used for this. So for in this case, like FPGA, if we use a different type of fixed point data type, it will also occupy the amount of resources in our FPGA device. So how we can do this? We have a tool, fixed point designer, that help us to easily or quickly come up with the optimized fixed point representation of for our algorithm. And then at each stage of this conversion, we can easily verify again with our golden reference or the floating point algorithm. Then we can see how accurate or whether it still meet our error of tolerance for our system. So in terms of a wireless design, there's a way to help ease this process of transitioning from our golden reference to for hardware implementation. Basically, we have a tool called this wireless HDL toolbox. Where it provides the hardware-friendly the algorithm that target for this like FPGA device. So in this wireless HDL toolbox, it has numerous blocks for you to design your wireless system, whether you want to design like a 5G LTE wireless LAN. Also, it comes with this reference application and IP block that allows you to quickly use in your design stage. Okay, so you can also use this block, and then you can compare with the golden reference and see how accurate and this block the system run the system performance. So let us take a look at this the next step here. Basically, once we in this simplified model, basically we have algorithm 1 and algorithm 2 that we want to target to the hardware. So in this case, maybe for algorithm 1, we want to target to the FPGA. Like I mentioned, we have this tool called HDL coder, help us to generate the HDL code from our algorithm or Simulink model. Okay, so algorithm 2, basically we target for this embedded processor. So we generate the C++ code. Okay, so once we have this algorithmic code, we can directly it may or may not work perfectly to our particular hardware. Okay, what I mean here, because in the hardware platform itself, there are numerous peripheral that we have not taken into account in our system simulation. So in this case, suppose like there's this a memory model, the interconnection, and various this I/O port. Okay, that it might cause the a certain performance or certain issue when you just directly deploy your code to this particular hardware. So in this case, it's a good idea if we can simulate these various peripheral or hardware architecture in order to have a better uh, accuracy of our system modeling and simulation. So this is what we want to discuss in the next aspect here. Okay, so how we can model this the entire system, including the hardware architecture, like the external memory that we being used, or the connection between this FPGA and this processor through this XC register. So we can model this using the SoC Blockset library. Okay, so we can model various I/O ports. So in this case, we can see. Okay, so the step here, basically we simulate the hardware architecture together with a algorithm. Okay, then we deploy to this particular FPGA or SoC platform. Then we can do the profiling. Okay, so the profiling here, like understand the effect of OS or the scheduling that being used, and also we can see the performance or hardware utilization of our algorithm for this particular hardware or device. Okay, so let me show you this step here. So the next step here, once we can model this entire thing, then is we can deploy to do the standalone implementation. Okay, so where we already take into account not only the algorithm aspect, but also the interconnect aspect of this particular hardware platform. So this is typically being done. We have this reference design for a particular hardware platform. So we can see in the next slide one simple example or model that how we can do this modeling or development for this the hardware. So in this example, basically, I have this 5G and R cell search reference application. Okay, in this case, basically, the cell search algorithm will be deployed to the hardware, okay, or the FPGA. Then we also have the search control or running in the software part or the ARM processor. Okay. So what this software, it will output this frequency, offset, and subcarrier spacing as the input to this cell search algorithm. Okay, so if we look closer, let me see. So once we for this example, once we run, basically for this cell search, it will find out this the SS grade, the PSS. If you are not familiar with this, basically the PSS signal is the primary synchronization signal, and the SSS is the secondary synchronization signal. Basically, it's for the user equipment to obtain the cell identity and this, the timing. So we'll take a look closer at how we can design this kind of system. Okay, so like I mentioned earlier, basically in wireless SDL toolbox, we have this reference example that you can directly use that already hardware friendly. Okay, so like the model already in a fixed point. Then you can you can use this model. You can inject the stimulus, okay, the signal from you design from either from MATLAB, and then you can compare this particular the implementation with your maybe your MATLAB golden reference, and you see verify the result. Okay. So this step is this verification is typically is important, so you can see what's the effect. Okay, so you can see on the right side how we can verify this particular algorithm with a MATLAB golden reference. We can verify it so that we can observe the latency and the quantization effect from this the fixed point architecture, okay, that being introduced. Okay. So once we tested this particular algorithm, the next step is simulation of this. We can also together bring the RF signal portion, so we can have a complete simulation. Okay. So in this demo example, basically, we model the entire the same example, the 5G and RF cell search for this particular device, the Xilinx RF SoC device. Okay, so in this model, basically we have this and first. These are the FPGA portion. We model the memory interface and also the processor, and this the RF data converter. So this is a representation of this Xilinx RF SoC device model. So if we take closer look at this FPGA subsystem, basically we can see that how we implement this receiver, the just now the cell search receiver. Okay, so yeah, this is for my FPGA algorithm being run in these FPGA devices. Okay, so this will output the cell ID. Okay, and then for this okay, so this is the part for my processor. The algorithm running in this processor basically consists of this task manager and this ability to the connection with our host computer. Basically, what it will return is this one. Okay, so once we simulate the entire thing, basically when we can see this the output, the PSS detection and the location of it, then the demodulation for PSS and SSS signal. Okay, so once we can simulate the entire system and including these various peripheral like memory and these various I/O and register, okay, then we can gain confidence. Then we can directly implement this on the hardware itself. Okay, so in order to implement to the hardware, basically, like I mentioned, we have reference design that are being provided. So in this two links on this slide here, basically the Xilinx support for this SoC platform, like one of it, the Xilinx SoC device, and different various Xilinx FPGA device as well. Okay, so in case if you need this information, then yeah, later you can take a look at this two links. So with this reference design, it helps you to not only being able that generate your code and target to these particular devices, so you can directly generate the bit stream, then work for this particular hardware. So let me show you this is the implementation with the real device. Okay, just now is the behavioral or model of this RF SoC. Okay, now in this example, basically I programmed the RF SoC. Okay, for the same example or same algorithm. So basically connect to this 5G and self-source algorithm model, the hardware, to the real hardware, and generate the bit stream deployed to this RF SoC device. Then same thing, once you run, you can see that these various analysis of the output, like hardware state of this particular device, and let me pause a bit here. The return value of this PSS SNR, the SS SNR, and the decoded cell ID. Okay, so the connection with the host, like I mentioned just now, is through this UDP port. So this is how we can model the entire thing or the SDR platform. Okay, so from the model itself, then we can simulate also the hardware architecture, and then finally we can generate the code and deploy to the real device. So before I show you other slide of various SDR or reference design for various SDR platform. So this is just one user story also from other customer. The RF pixel, basically they adopt the same workflow that I show you just now. Basically they try to test the LTE their golden reference model in MATLAB and Simulink, and then they deploy to this same device, the RF SoC board, for over-the-air testing. So basically using this HDL coder to help them generate the HDL code, it saves them the effort of design iteration from weeks to days. Okay, so this is a slide that I mentioned. Basically, beside the RF SoC device, so these are various device that we provide the reference design that you can directly use for in terms of your SDR development, from ADI, RF SOM, the ZC706, and so on. So in case if you work with other customized SDR development, there's also a number of reference example that can guide you or to help you get started for designing with MATLAB and Simulink. So you can see for various standard like a 5G, okay, LTE, or even the custom communication system like AD, SB, Transceiver, and so on. Okay, so in the last slide here, to summarize and also to provide you more information. So to summarize, basically we see that how we can use a MATLAB Simulink as a unified platform for wireless design, modeling, and development. So from the system level modeling and going towards the hardware implementation, okay, we can see that how we can target the hardware like FPGA and the software, the processor part. Okay, so we can also see how we can use different tool to connect to different various instrument for doing the over-the-air testing. Okay, and numerous support package for this SDR for you to quickly develop your system. Okay, so to get more information, if you are interested to know more about this typical workflow or model-based design workflow that I covered just now, we have this dedicated page for this software-defined review. So you can go to this page, and there are numerous information like a white paper, example, and videos to guide you through. And in case if you are working particularly for this RF SoC device, we also have this page dedicated for this particular platform. Okay, there are numerous examples as well.